Two data centers, one in New York, one in London, both holding the same bank account balance. For 1 exact second, the network cable between them goes dead. In that 1 second, someone in New York tries to withdraw the last $500 in that account. The database has to answer right now, and whatever it answers next will either be provably correct or provably available. It cannot promise you both. That's not a bug anyone wrote. It's mathematically proven to be impossible. By the end of this video, you'll know exactly why that's true, which choice your own database already made for you without asking, and the two-question framework real engineers use to decide this for themselves. Before any of this matters, it helps to ask why a system would run on more than one machine in the first place. Usually it's for one of two reasons: scale, because one machine can't handle every user in the world fast enough, or safety, because if that one machine catches fire, you don't want every copy of your data to disappear with it. So real systems copy data across multiple machines, sometimes in the same building, sometimes on opposite sides of the planet. And that's exactly where the uncomfortable fact shows up. Any system running on more than one machine is, sooner or later, going to lose the connection between those machines. Not because someone made a mistake. A cable gets cut, a router hiccups, a data center loses power for a few seconds. When that happens to two machines that were talking to each other, computer scientists call it a partition. The network splits into two islands that can't hear each other, even though both islands are still running fine on their own. The moment that happens, each island has to decide, completely on its own, what to tell the person standing in front of it. In the year 2000, a computer scientist named Eric Brewer proposed that any system like this can only really promise two things out of three possible guarantees ever. The first is consistency, meaning every single read from any machine always returns the most recent write, as if there was only ever one copy of the data. The second is availability, meaning every request gets a response, period, even if that response has to be "I'm not completely sure, but here's my best answer." And the third is partition tolerance, meaning the system keeps working at all, even while that network split is happening. 2 years later, Seth Gilbert and Nancy Lynch at MIT actually proved this mathematically, which is why it's called the CAP theorem, not just a Brewer opinion. Notice what's missing from that list. Speed isn't one of the three letters. A system can satisfy this theorem perfectly and still be slow. CAP was never a promise about performance, only about what happens to correctness and uptime specifically during a network split. Here's where almost every explanation online quietly gets it wrong. They say pick any two of the three, as if partition tolerance is some optional feature you could just turn off if you wanted perfect consistency and perfect availability together. But a real network is going to partition eventually, whether you want it to or not. You don't get a vote on that part. So the actual choice only exists in that one moment when a partition is actually happening. Each island of your system has to decide between staying consistent, which might mean refusing to answer until it can confirm it's not out of sync, or staying available, which might mean answering anyway, and risking that the answer is a few seconds out of date. Back to that bank account. The New York side can freeze the withdrawal until it reconfirms the balance with London, consistent, but the customer standing there gets nothing. Or it can let the withdrawal go through based on what it saw a second ago, available, but if London already paid out the same $500 to someone else, the bank just lost money it can't get back. The same exact shape shows up anywhere two copies of the same number exist in two places: an online store with one item left in stock, shown on two different servers. During a partition, one server can refuse to sell it until it reconfirms the count, consistent, and risk losing a sale to a customer who gave up waiting. Or both servers can let the sale go through, available, and the store ends up promising the same last item to two different people. Now, that split-second decision your database makes isn't random. It was already baked in by whoever built it, years before your app ever existed. The real question is whether that choice actually matches what your app needs. And to answer that honestly, you have to look at what real systems actually do, and where a lot of popular explanations, including this one so far, are still oversimplifying. Some databases lean hard toward consistency. Systems built around a single leader, like a traditional relational database, or coordination systems like Zookeeper and ECT, will refuse to confirm a write until enough machines agree on it, even if that means an occasional "please wait" during a partition. Under the hood, most of them rely on a consensus algorithm, Raft or Paxos, where a write only counts once a majority of machines, a quorum, have confirmed it, which is exactly how they stay correct without needing every single machine to be reachable at once. Other systems lean toward availability. Cassandra and DynamoDB were built specifically so that every node keeps answering requests during a partition, accepting that two different machines might briefly disagree about the latest value, and sorting the disagreement out later. Neither choice is wrong. A system tracking bank balances leans consistent on purpose. A system tracking how many people liked a video leans available on purpose, because a like count being off by a few for 10 seconds costs nothing. Some systems don't even force you to pick once globally. Cassandra lets you choose a consistency level on every single read or write, ask only one machine and get an answer instantly, or wait for a quorum of machines to agree first, so the same database can behave more like an available system for one query and more like a consistent one for the next, depending on what you actually ask it to do. Here's the part that most CAP explainers, including plenty of interview prep content, never mention. Computer scientist Martin Kleppmann pointed out something important in 2015. Almost no real database is cleanly CP or AP the way the theorem describes. The proof itself only covers one single piece of data being read and written, not the multi-step transactions real apps actually run. It says nothing about a slow network, a crashed disk, or a buggy deploy, only a full, clean communication break. And in practice, different operations inside the exact same database can have completely different guarantees. On top of that, there's a trade-off CAP doesn't even mention. Even when the network is perfectly healthy, with no partition at all, replicating data to multiple machines still forces a choice between waiting for consistency and responding fast. That's the extended version of this idea, called PACELC, and it's actually the trade-off your system lives with every single day, not just during the rare partition. So here's the practical version, the one that actually matters when you're the one designing the system. Ask two questions. First, if this piece of data is a few seconds stale, what actually happens? For a follower count, a view count, a last seen online timestamp, nothing bad happens, so you lean available, and let the system answer fast even with slightly old data. Second, if this request fails outright instead of maybe being wrong, is that safer? For a bank balance, an inventory count you're about to sell out of, a seat you're about to double book, yes, a clear failure is safer than a wrong success, so you lean consistent, and you accept that sometimes the system has to say try again instead of guessing. Most real systems aren't one single answer for the whole app. They're dozens of these small decisions, made operation by operation, exactly the nuance Kleppmann was pointing at. A single checkout flow might stay strictly consistent for the payment step, and switch to available for the customers also bought recommendations underneath it. Same app, two different trade-offs, chosen on purpose. Walk through an actual checkout page with this lens and it splits apart cleanly. The payment charge itself consistent, because charging twice or charging nothing is genuinely dangerous. The stock count shown on the page, often available, because showing 12 left, when it's actually 11 for a few seconds doesn't hurt anyone, and refusing to load the page while confirming the exact number would hurt a lot more. The recently viewed list, fully available, because nobody has ever been harmed by a slightly outdated recommendation. Same page, three different pieces of data, three different answers to those two questions. Consistency, availability, partition tolerance, and the two questions that actually decide which one you give up, and when. That bank account from the beginning of this video wasn't a flaw in some engineer's code. It was a choice, made deliberately, by someone who understood exactly what they were trading away. Once you can see that choice happening, you stop treating distributed systems like magic, and you start treating them like exactly what they are, a series of specific, nameable trade-offs. If you want to see one of those trade-offs play out inside a single machine instead of across a network, go watch our video on the event loop next.